Okay, calculating and using equilibrium constants. Changes to a system at equilibrium cause equilibrium to shift to oppose the change. Le Chatelier's principle is the guiding principle behind this. The equilibrium constant will remain constant under these conditions with the exception of a temperature change. The value of the equilibrium constant, or the KEQ, can be determined if the equilibrium concentrations in moles per liter are known, and the K expression is known or can be determined from a balanced chemical equation. For example, hydrogen and iodine react to produce hydrogen iodide. Concentrations at a certain temperature are 0.442 moles per liter for hydrogen, iodine 0.442 also, and then hydrogen iodide 3.116 moles per liter. Now the square brackets indicate that these are concentrations, and the AQ tells you that these are equilibrium concentrations. Equilibrium concentrations can go into the equilibrium K expression here. So you set it up first, make sure you write it out, then plug in your numbers and do the math. So the beauty of this is we don't have to worry about our units for K in this unit. In rates we did, but in equilibrium we don't have to worry about it. So this equilibrium constant is equal to almost 50. So this actually favors the right hand side, the products. There's way more products at equilibrium than there are reactants. So let's do an example. 1 mole of ammonia is injected into a half-liter flask. At equilibrium, there's 0.80 moles of ammonia, 0.30 moles of hydrogen, and 0.10 moles of nitrogen. What is the value of the equilibrium constant? Well, we haven't been given the reaction, but we do know which entities are present, and we know where it started from because NH3 ammonia was injected into a flask. So we're starting with ammonia, so it will decompose into hydrogen and nitrogen gases. So now let's balance this. Okay. When we put the information into our equilibrium expression, it has to be in concentration. It can't be in moles, so we will have to find the concentration for all of these. But we can write out our K expression now, and it will be the products over the reactants. So we have hydrogen on the right, so it'll be third order. N2, and that will be first order all over ammonia, and that will be second order. Now, 0.8 moles divided by half a liter is equal to 1.6 moles per liter. 0.3 becomes 0.6. And 0.1 becomes 0.2 moles per liter. All right, so now we can plug those values in. So 0.6 cubed, 0.2 to the first order, and then ammonia is 1.6, and that is squared. So this is equal to 0.216 times 0.2 divided by 2.56. So this is equal to our equilibrium constant is equal to 0.017. No units required. So this tells us there's way more reactants at equilibrium than products, so our equilibrium lies to the left. The lying part is based on the arrows in the equation, so the equilibrium lies to the left with ammonia. Okay, things to remember. Our equilibrium constant is the concentration of the products over the concentration of the reactants. We have to use moles per liter concentrations, and the reaction is elementary, so the coefficients are the exponents in the equilibrium constant expression. If the reaction is homogeneous and contains gases, partial pressures can be used instead of molar concentrations. However, if a KEQ is given, it has to be converted to KP. But the K used for our K expression will be a KP. So KP will be the partial pressures of the products over the partial pressures of the reactants instead of the concentrations. And then to convert to KP, if you're given a KEQ, then it's just KEQ times RT, the gas law constant, times the temperature, all to the exponent, which is the sum of the coefficients of the products, minus the sum of the coefficients of the reactants. But you won't have to worry about that, is my guess. Okay, so water is decomposed into oxygen and hydrogen gases. Okay, we're going to assume that that's water vapor. All right, so water vapor, H2O, decomposes into oxygen and hydrogen. So, at equilibrium, the partial pressures are, okay, so Kp would be the partial pressure of oxygen times the partial pressure of hydrogen squared over the partial pressure of water vapor, also to the second order. So it is just like before when we used our concentrations. So Kp is going to be equal to 2.67 times 1.15 squared over 0.63 squared. So this is equal to 8.9. So our equilibrium lies to the right with our products because this number is greater than 1. So that means there's more products than reactants. Often, we only know the initial concentrations of the reactants, but we do not know the equilibrium concentration of the products or the reactants. We can determine the concentrations by understanding the changes that the system goes through to achieve equilibrium. We can use ICE tables. ICE stands for initial, change, and equilibrium. And a known equilibrium concentration, or our equilibrium constant, can be used to determine the unknown concentrations. And I've given you some steps to follow. Step 1, write a balanced chemical equation. That's a must. Step 2, write ICE vertically and put your initial concentrations for the start of the reaction. Because it's at the start, you have 0 product. This is right at the beginning. Step 3, now you're going to put in the change. We're going to let X represents the change, and we're going to multiply it by the coefficient for the substance. Products are positive and reactants are negative. So if you're a reactant, like in example 1, we had 1 hydrogen as a reactant, so the change is negative 1x. But when we have 2 hydrogen iodides in the product, the change is going to be plus 2x. Step 4, you're going to add the the initial and the C line from the ice table together to make up the equilibrium E concentration line of the table. So example 4, when ammonia is heated, it decomposes. When 4 moles of ammonia is introduced to a 2-liter container and heated, what are the equilibrium concentrations of hydrogen and nitrogen if the ammonia equilibrium concentration is 1 mole per liter? So first thing was to write a balanced chemical equation and then write ice vertically. So we have to put in our initial concentration. So we have 4 moles introduced into a 2-liter container. So 4 moles, a 2-liter container. So our concentration is 2 moles per liter. And that is for our ammonia. Okay. So underneath ammonia on the I line, we're going to put 2.0. You don't have to put the units in. Initially, there's 0 products because the reaction hasn't started yet. So then it undergoes a change. Because ammonia is a reactant, it's negative X. And you put a 2 in front because there's 2, a coefficient of 2 in front of ammonia. So then your products are plus. So nitrogen will be plus 1x, or just plus x. And hydrogen will be plus 3x, because there's a coefficient of 3. And then the E line in the ice table, you add up the I and the C. So 2 minus 2x. And this is 3x plus 0, and this is x plus 0. So at equilibrium, we have 2 minus 2x for ammonia, 3x for hydrogen, and nitrogen is x. So we need to solve for these concentrations. So we've got to figure out what x is. Now, we're also given that we know the equilibrium concentration of ammonia. So the concentration of ammonia at equilibrium is 1 mole per liter. But we also know that from our table it is equal to 2 minus 2x. So what we do is we solve for x. So 1 is equal to 2 minus 2x. So 2x is equal to 2 minus 1. Divide both sides by 2, and you solve for x. So x is equal to 0.5 moles per liter. So now we know what x is. We can solve for the equilibrium concentration of hydrogen by substituting it in. So H2 at equilibrium is equal to 3 times x. X is 0.5. So hydrogen is 1.5. 3 times 0.5 moles per liter. Nitrogen at equilibrium is equal to x, so this is equal to 0.5 moles per liter. So we know the concentration of hydrogen at equilibrium. We know the concentration of nitrogen at equilibrium, and we know the concentration of ammonia at equilibrium. So this is an example where we were given one of the equilibrium concentrations. We could also solve for x. If we were given the K value, we would substitute in our numbers and solve for x. Okay, example number 5. Hydrogen and bromine react to form hydrogen bromide. If the K equilibrium, so the equilibrium constant is 120 at 150, and there are initially 4 moles of both hydrogen and bromine placed in a 2-liter container, what are the concentrations of everything at equilibrium? So the first thing we need to do, and I'm going to rewrite it, is put in our balanced chemical equation. All right, now what do? We set up an ice table. Okay. So initially we had 4 moles placed in a 2-liter container, so initially we have 2 moles per liter, right? 4 moles divided by 2 liters is equal to 2 moles per liter. So 2.00, 2.00, and at the start we have no product. So they go through a change, so negative x, they're being used up, and we're producing 2x. So at equilibrium, we have 2 minus x and 2x. We're given the KEQ, we're not given a concentration, so this is the other way to solve it. So KEQ, and always write this part out. Don't skip and start plugging in numbers. Write out your K expression properly, and then substitute your values. Okay, so I just made that smaller so we can see. All right, so now we're going to substitute in. We have, for HBr, at equilibrium, so we're taking the information always from our E line in our ice table, because that's at equilibrium. So we substitute in these values. So we have 2x, don't forget to square it, over 2 minus x, 2 minus x. Now, you should know that chemists are not lazy, but we are efficient. So if we can simplify this so that we don't have to use the quadratic method, we will. So this becomes 2x squared over, we can change the bottom to 2 minus x squared, because there's 2 of them. Squared, that's 2. And this is equal to 120. Okay, so let's simplify this. If I could take the square root of both sides, I end up with 2x over 2 minus x, and that's equal to the square root of 120, which is 10.95. Okay, so 10.95 times 2 minus x is equal to 2x. So 21.9 minus 10.95x is equal to 2x. Just did a little bit of algebra. Move our x's to the same side, so 21.90 So add 10.95x to the right-hand side, so we get 12.95x. Divide both sides by 12.95. And we have our x. So our x value is equal to 1.69 moles per liter. We're not finished yet because the question asked for what were the concentrations at equilibrium. So now we plug 1.69 back into our E line. So the concentration of hydrogen is equal to the concentration of iodine at equilibrium, which is equal to 2 minus x. So 2 minus 1.69. So their concentration is 0.31 moles per liter. The concentration of HI is 2x. So 2 times 1.69, so 3.38 moles per liter. So here we have our equilibrium concentrations solved for this question. So that's basic calculations to find equilibrium constant values or the equilibrium concentrations of our entities.